the derivative of a logarithm that has a log base 3 right here, as well as a natural logarithm. So it's a little bit of a combination type problem. So we're going to use both of our rules. We'll end up using the rule for the natural logarithm equaling 1 over x, x greater than 0. And then we're also going to use the rule that the derivative of a log base a is equal to 1 over x times the natural logarithm of a, and again, x greater than 0. So our outside function happens to be the non-base e logarithm. So what I end up with is y prime is equal to 1 divided by my argument right here. My argument is that, so divided by 1 plus x ln 3 times, let's extend our line here, the logarithm of the base, the natural logarithm of 3 right here. See, that's right here, x ln a times, right there. There we go. Now that takes care of my outside function, but I also have to use a chain rule to take care of my inside function. Well, the derivative of that, I'm going to actually do that over here as a little tangent, and then we'll put it up in this spot right there. So I have x times ln 3, and I have to take the derivative of that. So I want the derivative with respect to x of this. The thing you need to realize here is that the log of 3 is a constant. It's just a number. I'm asking a question, what exponent do I need to put on e to give me the answer of 3? And it's going to give me a number as an answer. So that can just pull right through the derivative. So really what I have is ln 3 times the derivative with respect to x of x, and of course that's just 1. So the derivative of this whole expression right here is simply ln 3. Now think about that for a minute. Pause the video. Think about that. So if that's the case, then this ln 3, which is the same thing as ln 3 over 1, cancels out that ln 3. And so my y prime is simply this piece right there. 1 divided by 1 plus x log 3. Now, let's talk about the domain for a minute. In my original function here, I know that the argument of a logarithm has to be greater than 0. So the argument of the logarithm is 1 plus x ln 3, and I have to make that greater than 0. Not greater than or equal to, but greater than. So I'm going to subtract 1 from both sides. So I have x ln 3 is greater than negative 1. And remember, ln 3 is just a number. So I'm going to divide both sides by ln 3, divided by ln 3. And I find out that my domain is that x has to be greater than 1 over ln 3. Now, that is the domain for the function right here. If you just take a look at the derivative, well, really in the derivative here, x cannot be equal to 1 over ln 3, negative 1 over ln 3, because that would give us a 0 denominator. But when we're trying to find the domain of the derivative and the function, if I can't have a number in the function, then there is no number in the derivative. The derivative does not exist where the function does not exist. So our domain for the derivative has to be the most exclusive between itself and the function. So this is the domain of the derivative and the domain of the function. Let's do another quick problem that kind of combines logarithms and, in this case, exponential functions. So I need to find the derivative of this. Well, my x is stuck up there as an exponent, but it's the exponent of a logarithm. So I'm going to use the power rule and change this to x ln 10. So that's x times ln 10. This is the power rule of logarithms, not the power rule of derivatives. Sorry, this isn't y prime. This is just plain y. I just used the logarithm. I used the power of logarithms to move this to the front. So now if I find the derivative, well, this is just a number. And that number gets pulled right through the derivative. So it's equal to ln 10 times, well, the derivative with respect to x of x, but of course that's just 1. So the derivative of this whole function right here is simply ln 10.